All right, as we continue to expand the number of functions we can integrate, we're going to talk about the integrals that result in natural logs. And let's introduce this by talking about the power rule. And there's one exception. If you integrate x cubed, you get x to the fourth over 4 plus c. If you integrate x to the negative fourth, which is what 1 over x to the fourth is x to the negative fourth, that becomes x to the negative 3 over negative 3 plus c. And you could simplify that, but that's not the point right now. The point is there's one that we cannot do, 1 over x. That would be like the integral of x to the negative 1 dx. Well, add 1 to that and you get x to the 0. Not a big deal. Anything to the 0 equals 1, but then you have to put that 0 on the bottom also. So this is the one exception. This is not going to work for the power rule. Because of that 0, you should have known in various applications you can't have 0 in denominators. So the power rule doesn't work. It'll work for any power except negative 1. So here's the new rule. Just cut straight to it. The integral of 1 over x is natural log of x plus c. So this lets us integrate functions that have something to the first power in the denominator. And to generalize that, 1 over u du is the natural log of u, and that just involves u substitution. We need to have du there. And usually it's going to be in the form of u prime over u. So if you want one to memorize, this is the form that you want to memorize. And that the derivative of whatever the denominator is, it could be either written out here to the side or on top. Usually it's going to be on top. And this just looks the opposite of the derivative of natural log, which is u prime over u. So this is not a shocking result, but it is the one case of the power rule that doesn't work. So we're going to have functions to the first power in the denominator and the derivatives of those functions in the numerators. Here's a very common mistake. See it a lot in Calc 2 when it's been a while since you learned this. The antiderivative of natural log of x equals 1 over x. That is a very tempting thing to say. This is not true. And you can see it's just reversing this new rule that we're learning. We can integrate the natural log of x, but you need a method called integration by parts that we're not worried about yet. Either late in Calc 1 or early in Calc 2, you'll get that method. So don't integrate natural log of x. Just assume for now you cannot do that. Okay, so let's see some of the results, some of the functions we can integrate now that we know this new rule. We're looking for du over u, or we're looking for u prime over u. That's our goal. So in a case like this, I don't have the denominator like raised to the third, where I was going to do a power rule where the power was negative 3. I just have a function on the bottom to the first power. So the denominator is going to be u. And if that's the case, du, or u prime, is 2x dx. Now I almost have that on top. I need a 2 there and a 1/2 to counteract that 2. And my answer is simply 1/2 times the natural log of x squared plus 1. Now the formula comes with absolute values around the u. I should have written that on the previous screen. The answer, the integral of u prime over u, is natural log of the absolute value of u. And that's just because you can't log anything that's negative. If you remember the graph of a log, it only exists over on the right-hand side of the graph. So it's impossible to log anything that's negative. So usually we have to put absolute values. However, in this case, x squared plus 1 is never negative because x squared is 0 at its smallest. So 0 plus 1 is 1 at its smallest. And so I can change those absolute values to parentheses. Not necessary to do absolute values if the value inside could never be negative. Okay, so next example. U is the denominator, x cubed plus x. Du is 3x squared plus 1 dx. And I have that perfectly. So a lot of times in practice, I'll just call it du over u. Or u prime over u. Same thing. You just need the derivative on top of whatever function's on the bottom. So my answer is natural log of 3x squared plus 1 plus c. And for that same reason, I guess I don't need those absolute values because 3x squared plus 1 is always positive. That one didn't need any adjustment of constants. It was just good the way it was. Next example, we have some trig. So tangent on the bottom and secant squared on top. So look out for questions like this where the denominator is u and the derivative of tangent is secant squared. So it works out perfectly. So the answer, natural log of absolute value of tangent x plus c. So this du over u, those can be any functions including trig. And this last one is somewhat of a non-example. I want to include, just so you realize, we still have our old power rule in play. If u is x cubed plus 1, the difference between this one and the other ones is this squared. Right? I don't just have a function to the first power on the bottom, I have a function squared. So this is a setup that's going to work for our traditional u substitution power rule. Du would be 3x squared dx, which I have. So when I do my substitution, I get u to the negative 2 du, which becomes u to the negative 1 over negative 1, or negative 1 over u. And when I substitute back, negative 1 over x cubed plus 1 plus c. So don't just see any fraction and think, oh, that must be a natural log, because it might be a power rule like we've seen before, and it usually depends on that exponent right there. The natural log, that's going to be a 1. See this x squared plus 1 to the first, x cubed plus x to the first, tangent to the first. That's an indicator of using a natural log. All right, so a consequence of this is we can expand and learn the other 4 trig antiderivatives. You already know the integral of sine is negative cosine, the integral of cosine is positive sine. You should know those. But now let's look at something like the integral of tangent. If you express tangent as sine over cosine, which we can do, now we are in a situation, because one of these things is the derivative of the other thing, where we can use our new rule. Since, let's see, the derivative of cosine is negative sine, if I squeeze a negative here and here, then I've got a perfect du over u situation. I shouldn't use the letter u, but that's usually what we use for substitution. I should use a different letter here. But I have the derivative on top of the function. And anytime we have that, we have the natural log of the absolute value of the bottom. And it's negative because I had to squeeze that negative on the outside. So here is our rule for tangent. The antiderivative of tangent is negative natural log of the absolute value of cosine of u plus c. So here is a new formula to memorize. The antiderivative of cotangent, which we could do similarly, is positive natural log of absolute value of sine u plus c. So here's number 4. And then secant and cosecant, they're a little more complicated, but they can be proven with similar ways. The natural log of secant u plus tangent u plus c. And cosecant is negative natural log of cosecant u plus cotangent u, close that absolute value, plus c. So there are numbers 5 and 6. So now we officially know the antiderivatives of all 6 trig functions. So now you can integrate any of the 6 as long as du is in there. So if you see a single trig function inside the integration symbol, its argument should be u. Then that makes du 1/2 dx. So I need a 1/2 on the inside, and I need a 2 on the outside. So then I can substitute and get 2 times the antiderivative of secant u du. And we just wrote down that formula. That's 2, and the antiderivative of secant is natural log of secant u plus tangent u plus c. And I want to switch back to x land because I switched into u and I want to switch back into x. 2 natural log of absolute value secant x over 2 plus tangent x over 2 plus c. So there's using one of our 4 new rules for secant. This is the style of problem you want to do if you see just a single trig function. We're not going to do u equals the secant, because if that were the case, the derivative of u would be secant, tangent, and then chain rule 1/2, and I definitely don't see all of this stuff inside here. That's not the case, all right? When you see a single trig function, the argument should be u. And one to finish up, cosine over 1 plus sine. This is not what I was just talking about. I do not see just a single trig function inside, so I have to choose a different kind of u. And this is actually going to be the other new rule that we learned, which is the integral of u prime over u dx equals natural log of absolute value of u plus c. So if I have some function on the bottom and its derivative on top, which would look like this, u equals 1 plus sine of t, and if that's the case, du equals derivative of sine is cosine. So what I see here is du over u, and the antiderivative of that is natural log of absolute value of u plus c. And to switch back into x land, natural log of 1 plus sine of t plus c. And there we have it. All right, so that's going to finish this one up. A couple main rules. The antiderivative of du over u is natural log, and then the 4 extra trig antiderivatives, and that's going to expand the number of integrals that we can take.